Okay, so you're either doing this after the fact because you've missed class, or you've decided to get ahead and take a look at what's going on here. You don't have to do this right now. We will cover it in class. So how do we draw Bohr models of atoms and ions? To do this, we have to remember the basic rule of shells. So first equals 2 electrons max. Second equals 8 electrons max. Third equals 8 electrons max. Then we have to know how to translate or interpret the element box from a periodic table. So here we have the atomic number, which equals the number of protons. Down here, we have the atomic mass, which sometimes has a decimal after it because isotopes throw off the number and we get an average. So what we have to do if we have the atomic mass, we round to nearest whole number. And this is now called the mass number. Okay, now this is important because we can take mass minus protons equals your neutrons. So in the case of phosphorus, 31 minus 15 equals 16 neutrons. Then up here, we'll change the pen color. We have what's called the ion charge. The ion charge tells us whether it's going to gain or lose electrons to form an ion. If it's negative, it gains electrons from some other atom to form an ion, and if it's positive, it loses electrons by giving it away to some other atom. Okay, and the number in front of the negative or positive tells us how many it gains or loses. If we know all that, it's very simple to draw a Bohr model. The first thing we're going to start with is what's going on in the nucleus. So first thing, the number of protons. And we better label this up here, phosphorus atom versus phosphorus ion. So first we look at protons by going up and looking at the atomic number. There's 15. And between an atom and an ion, there's no difference in the protons, so we can do both at the same time. Then we look at the neutrons, which we calculate by subtracting mass minus atomic number or protons. In this case, we get 16. And then we have to draw in the electrons, and that's where we have to be careful because electrons will be different from atoms to ions. For the atom, we have to remember atoms always neutral, meaning number of protons equals number of electrons. So in this case, if we have 15 protons, we have 15 electrons. We just have to put them in the order that the Bohr model allows. That's 2 in the first shell. We usually draw 1 up, 1 down, and then we'll be able to fit 8 into the next shell. And we generally go around the quarter hours of the clock once. That gives us 4, but it can hold up to 8, so we go around one more time. Now altogether, we're up to 10 electrons, but we need 15. That shell's full, so we go to the next one out and add in the next 5 electrons till we have 15. Now this outer shell, remember, is what's called the valence shell. It's the outer shell that has electrons with W/electrons. The electrons in the outer shell are naturally called the valence shell. Now, for an atom to be chemically stable, it needs to have a full outer valence shell. So that means in this case, it should have 8 electrons, but it only has 5. So it has a choice. It can either empty that valence shell, so the next one becomes the outermost shell, or by giving away 5 electrons, or it can gain 3 electrons to fill it up. It's actually easier to find 3 electrons than to give 5 away. That's actually indicated up top here by the ion charge saying 3 negative, meaning it gains 3 electrons. So to draw the ion, we just start the same way. 1, 2, 3, 4. I figured you guys could continue with your own counting. And in this case, we're going to add 3 electrons that it will find from some other atom that likes to give electrons away. And to indicate that it has gained these 3 electrons, we put square brackets around it and a 3 negative. Now, it can gain it by stealing it, in this case forming an ion, or it can gain it by sharing it, which won't form an ion, but it will form a covalent compound. Okay. So that brings us to what is the difference between a molecule and a compound. The difference is very subtle, but it is relevant. So a molecule is simply one or more atoms bonded together in some way, whereas a compound is one or more different atoms bonded together. So if we were to use a filled-in circle to represent a nitrogen atom, and an open circle to represent an oxygen atom, and we were to have 2 nitrogens bonded together, we'll just indicate bonding by being in contact. This would be N2 gas. We could have 2 oxygens bonded together to equal O2 gas. Or we could have a nitrogen bonded to an oxygen to equal NO gas. And in this case, only this would represent a compound. Whereas all of them, because they're made up of 2 or more atoms, would represent molecules. So you could say all compounds are molecules, but not all molecules are compounds. So what is the difference between ionic and covalent molecules? This is going to become relevant because we will encounter them repeatedly throughout the course. Ionic molecules form between opposite ions, which form when the atoms give or take electrons from each other. Some common examples of ionic compounds are salt, potassium iodine, and calcium carbonate. Now, the definition for ionic compounds kind of varies because you can say it in many different ways. But we can go ionic equals a giver of electrons plus a taker of electrons. Givers, if we look on the periodic table, are typically metals. So ionic compounds form between metals, and takers, which are typically nonmetals. And when you give up electrons, you become positive, so it forms between positive ions. And when you take, you become negative, so negative ions. And positive are more accurately called cations, and negative are more accurately called anions. So you can see ionic compounds defined in these different ways. Something that forms between metals and nonmetals, positives and negatives, cations and anions. In contrast, covalent molecules form between nonmetals. Nonmetals are typically takers. You get two nonmetals together, no one wants to give, they both want to take, and the best compromise they can come to is they actually share their valence electrons. Examples in our body include oxygen, carbon dioxide, glucose, proteins, and DNA. Okay. Finally, all this chemistry has to relate back to the human body. And the most major elements found in the human body are best represented by remembering the mnemonic Isotopes. Okay. This is carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. And these are considered the major six because altogether they equal approximately 98% of our body mass. And we have many other elements in our body that are absolutely critical to our survival, but they're considered trace elements. If you look up here, the one thing you'll notice they all have in common, and hydrogen can sometimes be placed over here, is that they are all nonmetals, meaning they form covalent compounds. So the vast majority of the compounds in our body are covalent, but the ionic ones that exist are absolutely essential to our survival. If you have any questions, you can come see me at lunch or ask me in class. Until then, I hope you have a good day, and I'll see you in class.